Hello, and welcome to the lecture for Chapter 11, covering the giant planets. These are Jupiter, Saturn, Uranus, and Neptune, the four gas giants. So let's talk about these last planets in our survey of the solar system. So here they are. Jupiter, closest of the gas giants, most massive by far. Saturn, famous for its rings, much less massive than Jupiter, although not that much smaller, but much lower density in addition to just not having such a large core. But of course, moving on, we have Uranus and Neptune. Uranus with some very unique properties. If you recall our discussions on the unusual orbits of Mercury and Venus, well, we've got one other unusual planetary orbit, and that is Uranus. It has a famous orbit, and we'll talk about it in just a minute. Neptune, interesting in its own right because it is so distant. We'll see in just a minute the distances aren't evenly spaced by any means. Let's discuss these amazing giant planets. So a good place to start is with the numbers. If we're looking at one astronomical unit as our standard measurement of distance, that being Earth's average distance from the sun, then look at the multiples of how much further the planets Jupiter, Saturn, Uranus, and Neptune, the gas giants, are. Jupiter's 5.2 AU. Now, to put that in perspective, if you recall Mars had a distance of about 1.6. Mars was not that much further, and that's the furthest out of the four terrestrial planets. In other words, the terrestrial planets, being Mercury, Venus, Earth, and Mars, are crowded together in an overall radial distance of 1.6 AU. But then we jump out to Jupiter, over twice as far, almost 3 times as far. But what about Saturn? Saturn, you could approximate roughly, is twice again as far. Look, it's double the distance. It was a large gap to get to Jupiter. The gap to Saturn is enormous. Travel time, probes being sent by humans, just ideas about how future travelers would take to get from one planet to another. These are unbelievably vast distances. And finally, look, we double again, this time truly, to get to Uranus. The distances are just scaling up more and more. And then half again as far to get to Neptune at 30 AU, 30 times further from the sun than Earth is. The sun is just a particularly bright star in the sky from the perspective of Neptune. That's how far out Neptune is. It has an orbit of many Earth years, and a number that we'll see in just a minute. It's just such a distant, cold planet, but still interesting things happening just because there's so much matter crammed together. These planets are massive and they're driven by gravitational forces and the consequences of those gravitational forces in dramatic ways that terrestrial planets just don't see. Oh, more numbers real fast. I'm spending enough time on it, I know, but I want to summarize these numbers. If we're looking at the period, the number I just hinted at, we see that Jupiter has a rather long orbital period, 11.9 years, Saturn, 30 Earth years, Uranus, 84.1, but of course, Neptune being so dramatically far has an orbit, there's 164.8 Earth years. So each quarter year is about 52 years. We'll see that when we break up its unusual orbit. So interesting numbers there, but of course it does make sense. If these planets are so far, they do have to have long periods. And we know this just from the fact that we have t squared proportional to the radius cubed in Kepler's third law. So we know they're going to be long periods. We can look at the actual diameter of these planets to see their size. Indeed, Jupiter and Saturn, they're close in size, but as I said, Jupiter's much more massive. We see that in the next column. And then if we look at Uranus and Neptune, their size is actually much closer together, as are their masses. So they really have a lot in common in terms of their both size and mass. The same can't be said for Jupiter and Saturn. In other words, you can't really group Jupiter and Saturn together. They're very unique planets. Not to say Uranus and Neptune aren't, but they have more in common. For example, Jupiter, here it is, has a mass that is 318 times the mass of Earth. That's a huge amount. That's not a million times like the sun by any means, but it is still a huge difference, especially compared to Saturn, which is only 95 times as large, okay, in terms of its mass. And its density, as I mentioned, the density of Jupiter is quite high, but so is the density of Uranus. Neptune being even higher, just a denser planet in terms of the materials it's made out of. Basically, it has less outer layers of very low dense molecular hydrogen and helium. But we'll talk about that when we talk about the layers of the planet. But most noteworthy is that very low density of Saturn. Saturn has a very uniquely low density. It's famous for being the only planet that would float, because the density here, measured in grams per cubic centimeter, is sort of normalized to water, where water is the value of 1 gram per cubic centimeter. So we can see Saturn actually has a density less than water. And finally, its rotational hours. The thing to note here with the rotational hours of these planets is how low they are. We talked about these planets that have very slow orbits with the terrestrial planets, especially Mercury and Venus. Venus most dramatically has a very, very slow rotational rate. And we might think and might assume these very large planets out in the distant solar system, they might also rotate very slowly. Their years are very long after all, but they actually all rotate extremely quickly, especially considering their size, to the point that their actual velocities on their surface dominate some of the physics of movement of fluids and gases at those upper layers. And also with Jupiter, we'll talk about the very fast trapped charged particles in Jupiter's magnetic field that are essentially speeding at ultra high speed in loops around the planet. But this is all driven by a conservation of angular momentum and how these planets are formed. So much gas came together in their formation that they actually have very large velocities from conservation of angular momentum. That's the explanation, the basic explanation of these large numbers. And I guess large numbers, I'm thinking velocities that are a consequence of these. In this case, we can think of them as a very short time. I mean, look, Jupiter's day, the time it takes to rotate all the way around its axis, a planet that's 318 times as massive as Earth, is only 9.9 hours, less than half of the day length on Earth. This planet is really spinning quickly. All right, Saturn's not very much different at 10.7. Uranus and Neptune do rotate a little bit slower, but all faster than Earth. Okay, here we have Jupiter, the most massive, dramatic planet in the solar system. It drives some of the biggest behavior. It dominates the gravitational kind of behavior between planets, being a planet that pulls in large errant asteroids and comets that thus don't make their way into the inner solar system. So, what are we looking at when we look at Jupiter? Well, we're looking at layers of clouds. We'll talk about the different molecules that make up the layers of clouds in this picture and the beautiful pole of Jupiter, but of course shown here in bands. We're looking at a band structure, noteworthy, which is explained by the very strong winds that themselves are part and parcel of the energy involved in the very fast rotation of these planets. There's that absolutely is connected with the fact that there's a lot of kinetic energy leading to very fast winds on the surface. And and because of the fast rotation, the fast winds basically smear out the storms, creating bands. Saturn has this too, but maybe less dramatically. Think of a rotational storm on Earth. But now imagine, to understand this idea of smearing out the storm, but then imagine that rotational storm, instead of just existing on a small parcel of Earth, is spread out over a much larger region because the planet is spinning so quickly. So that circular structure is smeared or spread out. And that's what we're looking at when we look at these bands. Now, there are exceptions. There are things like the huge self-contained storm that is the red spot on Jupiter's surface. There have been less stable storms even near the red spot, like the small red spot, that are also staying in place because there's probably so much energy in them they don't get pulled out. Maybe they have such a low pressure at their center. But regardless, the overall behavior are the bands. Here is a beautiful picture of Saturn as we're kind of continuing our pictorial survey of the gas giants to get more into this lecture. And we're actually looking back on Earth. So we can see this is actually a view of Earth as just a bright dot in the sky looking from, in this case, the Cassini spacecraft, I believe. Yes, so the Cassini space probe that was in orbit around Jupiter for some time, Saturn, and eventually crashed into Saturn at the termination of its mission. Okay. So let's take a look at Uranus because we're moving out in order. Here we see that Uranus also has rings, not exactly visible in the visible spectrum. We can't see them with the naked eye, but they do show up as false color images that are based off of infrared, so the heat signature that's coming out of the particles that make up the rings. In fact, all the planets have rings in terms of, all the gas planets. All the gas giants have rings, the four of them. So obviously Saturns are very bright, very reflective, but Jupiter also has rings that show up in the infrared, and so does Uranus. Okay? Now, you might wonder why these rings are completely tipped on their side. Well, that's often because we have here the ecliptic plane, and we'll be talking about that. Because rings, of course, are essentially in the equator of a planet. They have to be lined up with the rotational plane of the planet. Well, that means that the rotational plane of Uranus might be tipped. Indeed, it is. Okay, this image is here is showing many of the moons of Uranus existing not too far out spatially, not a much greater distance from the actual rings. Okay, all right, but these are the inner moons. Uranus does have some moons that are further out as well. Okay, so here it is, Uranus's unusual orbit. Okay, much like unusual orbits of Mercury and Venus, but completely unique in its own right. Because Uranus has, as we know, a very short actual rotational period. So we have a day that's shorter than Earth's. So in terms of the planet, it's constantly spinning, but it's constantly spinning on its side. In other words, its poles of rotation are completely 90 degrees knocked over from most of the other planets. Earth, for example, rotates on a pole that would face like this in the image. In other words, it's perpendicular to its orbit. But look, the pole of Uranus is parallel to the orbit. That means that at some points of the year, the North Pole, or in this case we see the South Pole, is actually facing the sun, directly head-on facing the sun. And then the sun would never set for the South Pole, because remember, Uranus's day is just a few hours, so the planet is booking around, quickly spinning, but the sun would just remain in the sky. Near the South Pole, at this particular time in Uranus's year, the sun would rotate along a particular altitude above the horizon, but just remain at that exact altitude in the local sky. Think about what the sun would look like from the equator at this point number 1, which we'll reference in the graph in just a minute. Well, a point along the equator, the sun would be perpetually right at the horizon, almost like a twilight, but also almost like a sunrise. The sun would just stay right at the horizon, the planet, and making a about 16-hour span, or 16-hour amount of time to go all the way around and come back to, say, facing the west, and that would just repeat over and over again for many, many days. Because remember, if we're talking days, this would be days of Uranus, so many, many rotations of the sun, if the path would almost not change. Because you have to remember that the year of Uranus is such that the time to complete, 1/4 of a year, which would go from here to here, so 1/4 of a full orbit, is about 52 years. All right, because we have 84 years to get to a point that is halfway through. So we should have 84 years. Let's look here. So this is 86 to 2001. So actually, this is a 21 year. All right, so I guess we have 21 years, of course, because I was thinking the orbit of Neptune. Excuse my blunder there. So the whole orbit is 84 years. That is the length of a year for Uranus. That's a Uranus year. And so each quarter of a year is 21 Earth years. Okay, so 21 to complete a quarter year, another 21 to get to the half year mark, and so on. Okay, so what then happens? I mean, that's a long time, right? That's a long time in Earth years. That's a lot of Earth days. That's a huge amount of days on Uranus. Well, finally, as we gradually change and we get to this part of the orbit, 1/4 of the orbit in, what part of the planet is now facing the sun? Well, the equator is. So now the planet is essentially in a perpetual equinox state for, again, many, many days. The entire planet would experience a day that has the same length. The sun would rise exactly to the east and then set exactly to the west, or maybe vice versa. I'm not sure which is which in terms of these two orientations, but one would be rising in the west and setting in the east, and the other would be the opposite. Other than that, though, it would just be that same day repeated over and over again for many, many days. At the poles, the sun would be right at the horizon, kind of like it was for the equator in our last point. And you see that then it takes a long time for that state to gradually change. So you have huge amounts of time where, say, one part of the planet, like the North Pole initially, at our point 1, was just facing away from the sun, getting no sunlight at all. So such an unusual day-night cycle, such an unusual relationship between days and years on this tipped planet, completely knocked over its side, Uranus, okay? So if we look then, we can see on this graph what the cycle would look like at the equator, right? Where the amount of sunlight, you'd have that equatorial amount of sunlight at the equator, like at year 2007, shown right here. And then you have a point where the equator is in perpetual twilight, right? The equator is never going to be in complete darkness, but you have a point where there's a minimal amount of light, because as we get to say 2028, that would be this point right here. The sun is just right along the horizon, and then we get maximum sunlight again at the equator, say when we get to 2049. Of course, the South Pole and the North Pole have more dramatic cycles where the light gets maximum, as we know about, say at this point right here, point 1, that corresponds to maximum light at the South Pole, and then that sun sort of disappears. So then we could get to a point like 2028, that would be over here, where there would be no sunlight at all in the South Pole, and then just the opposite for the North Pole. So very unusual cycle, very interesting. Now this just begs the question, why is this planet, the only one of the 8 planets, knocked over on its side like this? Well, the best explanation and theory is that it was literally knocked over. A large collision with some sort of protoplanet, some planet-sized asteroid, actually gave enough energy and hit in such a way that the planet, well, cooled down, because the planet has less internal energy than any of the other gas planets, and got knocked over on its side, or probably gradually went through a state where it fell over on its side. Now that we've done a quick survey of the 4 planets, compare some other information between them. We already compared their day length and their mass and so on in that previous table, but here with this figure, we're going to compare their layers. So we can see kind of the relative size. Of course, Jupiter and Saturn are much more massive than the smaller Uranus and Neptune planets, and we can see that they are composed of different things. Jupiter and Saturn have an upper layer that is mostly molecular hydrogen. Now, calling it molecular hydrogen is fair, but there also is a huge amount of helium. In fact, about 24% of the outer solar system, which is, of course, mostly the outer gas giants, the 4 gas giants, is helium. 24% is helium. So that means that although hydrogen is the vast majority of the remaining 76% or so, is that there's still a lot of helium. We don't talk about it too much, though, because helium is a noble gas, and it's not going to create any of the compounds that are famously identified on the planets, explaining their colors and so on in their atmospheres. So in that sense, it probably doesn't get the attention it deserves, but it is a significant amount of the outer solar system, with helium being about 24% of the mass of, really, you would guess, any of these planets, but certainly Jupiter and Saturn. Okay, so do take note of that. We will, you'll hear a lot more about hydrogen and its compounds. Now, as we then continue, say, our diving down into Jupiter, the next layer is a mantle, a liquid layer that becomes increasingly solid as we get deeper and have higher pressure, and that is referred to as metallic hydrogen. And the idea here is that hydrogen, when it is compressed into a liquid or solid state, takes on behaviors of a metal in terms of its free electrons. This is important because this explains how both Jupiter and Saturn have magnetic fields, because they need to have a large amount of free electrons in the same way that Earth has a large amount of free electrons in its metal core. And then those free electrons create a rotation of charge that then drives the magnetic field. So that's the explanation for Jupiter and Saturn having magnetic fields. Although it does beg the question, how are the magnetic fields of Uranus and Neptune formed? Well, there, I guess it's best to maybe think of a saline solution carrying a charge. In other words, salt water can conduct electricity. So it's best to think that the salty, icy slurry that makes up significant portions of the mantle or middle layer of Uranus and Neptune also allows for a huge amount of free electrons. And this ice, by the way, is best not thought of as ice that is, well, hydrogen, or dihydrogen oxide, or H2O, water, but instead think of this ice as methane ice, okay? So think of this as a frozen compound that is largely methane, okay? But still in a solid state, so we call it an ice. It's still a hydrogen-based molecule, methane is, so much like H2O. But there is some water as well, some H2O on any of these planets. Okay, so they all have layers, metallic behaving layers that form magnetic fields. We'll talk more about magnetic fields in a moment. Notice, though, that beneath the metallic hydrogen or ice layers, they all have a rock core. Those cores are larger than Earth, especially in the case of Jupiter and Saturn, much larger in the case of Jupiter, but they're much denser. They're basically as dense as Earth's core. And there's this huge amount of metal and rock that existed in the outer solar system in about equal portions as existed in the inner solar system, but then got caught up by the huge amount of gases and frozen hydrogen compounds that were available in the outer solar system. Because the solar system, as we talked about earlier in our overall view of the solar system chapter, is divided across a frost line. And the gas giants exist further from the sun than that frost line. And that frost line refers to the ability of hydrogen compounds to clump together because there is a cool enough space, cool enough portion of space out there. And thus they can then conglomerate by gravity and then form these massive planets. That process just wasn't available. The gases would be constantly evaporating and moving away where the terrestrial planets exist. Thus, the terrestrial planets had to form out of the only thing available, which was rock. So there's more available resources for these larger planets to form, which is why they form so much larger. But they still have rock at their cores. Okay, so these are the layers of the 4 gas giants. All lots of hydrogen, all lots of helium. Definitely some differences in terms of the smaller Uranus and Neptune planets. Now, we spoke about that magnetic field. Well, the most dramatic of all the 4 magnetic fields of the gas giants is that of Jupiter's. This magnetic field is one of the largest structures in the solar system. The magnetic field is larger than the sun, which is a pretty significant statement because the sun is much larger than Jupiter. But as magnetic field stretches out, it carries a huge amount of energy. You can imagine it's driven by this large amount of metallic hydrogen and all the charge in that metallic hydrogen, and the very fast rotation rate of Jupiter, as we spoke about before. So this strong magnetic field then traps charged particles in it. So there are charged electrons that exist some significant distance away from Jupiter, because in the scale of this photo, Jupiter would make up that inner portion. So we're talking 2 Jupiter radii from the center of the planet. We have these huge bands of charged particles. This actually is similar to the bands of charged particles that we know exist around other planets, including Earth. They are similar to something called a Van Allen belt, which will be a nice segue to briefly talk about Van Allen, the person whose last name is Van Allen. But regardless, tying this back in with the layers of the planets and their ability to form magnetic fields, we see here a dramatic example of a magnetic field. This huge magnetic field formed by Jupiter that encompasses many of its moons. Most importantly, this huge magnetic field of Jupiter encompasses the 4 large moons of Jupiter. These moons are so large that one of them, famously, Ganymede, is larger than Mercury. These are planet-sized moons, and they are within the magnetic field, which has huge consequences on both the behavior of these planets, but also the potential human habitability of these planets. There's interesting things to think about. Now, the last thing I want to say about the magnetic fields is that none of them are particularly aligned with the rotational axis, which is very different from the magnetic fields that we see formed by the terrestrial planets. Now, of course, the magnetic fields formed by terrestrial planets can be best summarized as Earth, Mercury, and very, very slightly Mars, or some evidence of past magnetic field on Mars. We don't see one on Jupiter. But at least if we're comparing between Earth and Mercury and notice our magnetic fields are almost perfectly aligned with the rotational axis, giving a direct story about how they're formed from the solid rock and the free electrons in that solid rock. But since the magnetic fields of these gas giants are formed by more malleable stuff, whether that's metallic hydrogen in a liquid/solid state, or certainly the slurry of ice and salt that carries charge within Uranus and Neptune. Well, whatever that reason is, it's more malleable. And so then the magnetic fields are not as well aligned with the rotational axis. The exception is Saturn. If we look at the magnetic field of Saturn, going back to the 4 planets, its magnetic field is fairly nicely aligned with its rotational axis, which is tilted relative to the ecliptic. So its magnetic field with a north and south end is pretty nicely aligned. Not so with Jupiter. It's fairly tilted in terms of actually tilted with the rotational axis. Interestingly, as we know, Uranus is tipped on its side, and its tipped magnetic field is almost backed up with the ecliptic. It's tipped so dramatically relative to the rotational axis. We might think that's just a special feature of it being tipped, but then Neptune has one that's tipped almost just as much, where its rotational axis is the more typical, almost no tilt relative to the ecliptic, but its magnetic field is tilted significantly. So the point is, there's a lot going on. There's a kind of a complicated story with these magnetic fields of the gas giants. So as I said, this idea of a band of charged particles some distance away from a planet is much like the named Van Allen belts of Earth, and these belts are named after the scientist and engineer James Van Allen, who was instrumental in the space race. He got up. He was a major member of the team that got up Earth's first satellite, following Russia's first satellite, which was humans' first satellite. But the United States was the next person to get the satellite, and he was, a big part of that. And then what was interesting is Earth's first satellite was Sputnik, launched by the Russians. But the second satellite that went into space, launched by the United States of America, that satellite did some significant scientific research. It was less of just getting up there as fast as possible. It had an objective in terms of the research, and that objective was to measure the hypothesized or theorized existence of bands of charged particles that were trapped in the same way as Jupiter, by the magnetic field, but in this case, the magnetic field of Earth. Well, they were discovered and confirmed, and there's a significant amount of charged energy that exists at a certain elevation, significant, but well above where most satellites are today. That is a band of charged particles. And it's actually a good thing to know about, because it affects space travel. There's always you have to pass that band of charged particles and acknowledge its consequences, because of course a lot of free charge can short out electrons, or electrics. But point being, it's a very interesting story here in terms of this individual. Okay, so moving on with the upper layers of these planets. So not concerned about their layers all the way down to their core, but instead concerned just about what we see, their atmosphere, if you will. Now, these planets don't have a surface, so sometimes it's strange to refer to their atmosphere, but this is the part of the planet that has low enough density that it behaves as a gas. It's not compressed into a liquid yet. Well, what are the atmospheres like of the gas giants? Well, Jupiter has colorful clouds. We see beautiful pictures of that. Saturn, of course, has its bands as well, a little bit more toned down, but Saturn makes up for it with its beautiful rings, which are shown here to actually show up as different views relative to Earth. So this is an Earth-based view of Saturn, and that's because of Saturn's significant axial tilt, which we saw just a minute ago. All right. But here are the actual molecules that make up the different levels of these atmospheres. So notice that both Jupiter and Saturn have very similar atmospheres in terms of their composition, and we can confirm these elements with spectral images, actually using the particular energy levels that come off of these molecules based on atomic and electron excitation levels, this idea of spectral images. Anyway, so what's the NH3? Well, NH3 is ammonia. So both Jupiter and Saturn has significant amounts of ammonia clouds. Now, why ammonia? Well, because of availability of nitrogen, and of course, hydrogen is part of that compound. Now, beneath the ammonia levels, or ammonia layers, both planets have ammonium hydrosulfide clouds that exist lower down. And then, both planets also, Jupiter and Saturn, have H2O, or water clouds, that are lower still. So real similar cloud layers, although the actual manifestation of the colors and the particular compositions vary significantly, as we can see. Okay, well, now let's take a look at Uranus and Neptune, because there's a big difference here. Because notice that here, both of these were driven by the abundance at the top level, the most visible level, of ammonia. Well, we don't see that on Uranus and Neptune. They're further out. We have different temperatures, different ability for gases to form. And out where Uranus and Neptune have formed, the upper atmosphere is instead mostly CH4, which you see in both of them, which is methane. Okay, so both of them have methane in that upper atmosphere. Now, above that are some hydrocarbon ices, okay, so labeled. But what's beneath that methane level? Well, we're not exactly sure, because this is hard to exactly detect, but scientists suspect that what they're looking at is hydrogen sulfide, H2S. All right, so a sulfur compound of hydrogen. Again, of course, hydrogen is there, but we have it bonding with sulfur. Now, in terms of hydrogen bonding with other elements than just nitrogen, which we see a lot of, right? and carbon, which we also see a lot of, what about these other compounds that are suspected to exist in the very upper atmospheres of Jupiter and Saturn? Well, those include, in the case of Jupiter, this N2H4, which is ammonium hydrosulfide. Okay, well, that's again just nitrogen and hydrogen coming together. But what's going on with this last upper molecular cloud in the case of Saturn? Well, this one's interesting because this is actually diphosphane, because here we see a molecule formed between hydrogen and phosphorus, which we haven't actually seen show up in any of these other images. So regardless, we have lots of hydrogen-formed compounds existing in these different atmospheres that give them their distinctive colors. Now, what's interesting is notice, is something I hinted at before, we don't see helium labeled anywhere. And that's not because helium doesn't exist in these upper atmospheres. But one thing is that the helium in the very upper atmosphere would likely have enough kinetic energy to escape. All these planets, except with the exception of Uranus, actually have a lot of internal energy. So there's a lot of energy in the high temperature, thus high velocity molecules. So the helium would likely escape in the upper atmosphere. But even in the lower atmosphere, where we might expect a lot of helium, it's there. But it's a noble gas. So it's not forming any of these large molecules that are allowed to clump together in clouds. So it just exists as a free atom, just helium by itself, existing within the overall mixture that is the spaces between the clouds. Okay? Now, what is interesting about the story of helium, though, in the case of Saturn, is that there's a significant amount of helium in the liquid mantle of Saturn. So well beneath the clouds, kind of going back to those other levels, those other layers of the planet. And that helium is actually continuing to differentiate. Essentially, it's clumping together and sinking in droplets through the largely hydrogen, basically ocean, liquid state that exists in the planet. Now, for whatever reason, we don't see this happening significantly on Jupiter, but that's probably just because of the different composition. Of course, they have different molecules that exist at different levels. They also can have a different composition mantle. But Saturn does, and that means that Saturn produces a lot more energy than any other of the gas giants. And all the gas giants output energy. They have a huge amount of internal energy left over. But Saturn has more than Jupiter. So the energy for Saturn is actually larger for Saturn than Jupiter. So again, that's because of the actual helium droplets that are sinking down to the mantle of the planet continually. So there's still essentially a leftover amount of helium that is denser than the surrounding hydrogen and is sinking down. But it's such a vast mantle on the scale of this planet that has been going on for some 4.5 billion years and still isn't done sinking. The planet is still settling, and that release of gravitational potential energy is driving the temperature of the planet. Okay? This extremely low density planet, right? And also one of the most energy producing ones. All right. So taking a look at the cloud structure of Saturn. The hexagon pattern on Saturn's North Pole, notice, right, that it actually looks like a hexagon due to these interesting shear effects of the fluid movement. Looking at Neptune and its cool blue color, remember that's driven by the abundance of the methane gas, all right? That gas that isn't common for Jupiter and Saturn, all right? High clouds in the atmosphere of Neptune. Look at these beautiful bands of clouds, okay? Now, we talked a while ago about the planets rotating so quickly. One effect that those very fast rotations have is incredibly high wind speed. The winds of these gas giants are extreme, and they're rather like patterned with huge bursts of wind along the equator in both Saturn and Jupiter's case, most dramatically for Saturn with its particularly high winds right along the equator, right? But then bands of lower winds in different directions, so some facing one way, others facing the other way, throughout the planet, going towards the North Pole and the South Pole for Jupiter, and the same sort of behavior towards the poles for Saturn. Uranus and Neptune also have these bands of very high-speed winds, but they're much more spread out. There's only a couple of bands. Okay. Now Uranus has almost a featureless surface, so it's hard to see these winds, and that's just because the planet is so cool and the surface is so solidified that the winds don't involve large cloud movements. Neptune does have noticeable cloud movements on its surface. Okay, here are those ongoing storms on Jupiter, these exceptions to the band's behavior of the planet, because so much energy is caught up in them. I mean, the giant red spot, the great red spot on Jupiter is big enough to contain all of Earth and then some. Right? Beautiful, beautiful picture of Jupiter's great red spot. Okay, well, this concludes our lecture on the four gas giant planets. I hope this lecture has been interesting and informative. Thank you so much for watching.